Okay, so this is the first example we're going to look at in section 3.7 on optimization problems. Okay, so example 1, a manufacturer is designing a container that is an open box with a square base. The total surface area of material needs to be 240 square centimeters. What dimensions will produce a box of maximum volume? So when it comes to optimization problems, the first thing that you want to do is going to be to draw a picture. So, well, in this case, the picture that makes the most sense is what does this open box with a square base look like. So we'll go ahead and start sketching that picture. So we have ourselves a box. Obviously, your box might look better than mine. We're going to imagine here that we have all of the sides exist except for the top. So now that we have our picture, we can label some variables. So we can label, say, this be the height, but we know since there is a square base that both of the dimensions of the base will be the same, and we can call those x's. So now that we have our picture drawn, now we're going to figure out what are some formulas that we can use to help us get to where we need to be. So one formula in this needs to be the volume of this box because it asks for what is the maximum volume. So we can write down the volume is equal to, in this case, the volume of a box is length times width times height, but because our length is x, our width is x, and our height is also h, our volume is x squared times h. So we always need to have the formula of the thing that we are maximizing. Now, sometimes we're going to have something called a constraint, where this constraint is going to restrict the choices that we have for what our variables are allowed to be. So in this case, our constraint is that the total surface area needs to be 240 square centimeters. Obviously, if we had as much materials as we want, we could create a gigantic box that would have gigantic volume, but we are restricted to only having 240 square centimeters. So we have to figure out what is the surface area formula for this shape. So our second formula that we will have is we will have our surface area. We have to have the area of the base of our box. The area of the base of the box is going to be x squared. We have the area of the four sides, which each area of those is x times h. We have 4 copies of that, so we're going to have 4 times x times h. And then if you didn't have an open box, you would also have the area of the top, but because we have an open box, we're not including that into our surface area. So that is our surface area formula. But because we know that must be 240 square centimeters, we can plug that in and say that we have 240 is equal to x squared plus 4 times x times h. So now looking back at the volume formula, our goal is to try to maximize that. So if we remember what we've been doing, we know that derivatives can help us maximize things. We can find the maximums, either local maximums or absolute maximums, or the same thing with minimums. So in this case, we're trying to maximize the volume. Our v is equal to x squared times h. However, we have 2 variables present, and that has not been something that we've dealt with at this point. So our goal now is going to be to solve. We're going to solve for h in terms of x. So this will allow us to turn our volume formula in just terms of x. So obviously the thing that we have available to us is this surface area formula here. We can now use this to solve for h. So once we solve for h, we'll see that we'll have 4x times h is equal to 240 minus x squared. We divide over the 4x, and we're going to have h is equal to a 60 divided by x minus x. Divided by 4. Oops. All right, so now we have this as our formula for h, so we can now plug this back into v. So now we see that v, this is now a function in only terms of x, so volume in terms of x is going to be x squared times 60 over x minus x divided by 4. So distributing this in, we see that our volume in terms of x is simply 60x minus x cubed divided by 4. So our goal now is to figure out, how do I find the maximum of this function? So you have to ask yourself, am I looking for a relative or a local maximum, or am I looking for an absolute maximum? Well, in this case, we're trying to find the box of maximum volume, so we would like to find the absolute maximum. Now, finding absolute maximums, we know that's easiest when we have a closed interval. So in this case, we'd like to figure out what would be our closed interval. So what would be a restriction on the smallest x can be and the largest x can be? So in this case, what we can do is we could now find some type of an interval for x. And what this is going to be called, this is called the feasible domain. These are the feasible values of x that make sense in the context. So what we see in this case is that x, because it's a length, we know obviously the smallest x can be is 0. Now the largest x can be, this is going to get a little bit trickier, but by a similar rationale, because h is also another variable, we know the smallest h can be is 0. So if we figure out what would this be, so if we went to this and we were to say if h is equal to 0, we can now calculate when h is the smallest, what is the largest x can be. Well, then we would have 0 is equal to 240 minus x squared, so we see that x would be the square root of 240. So we see that the biggest x could be is the square root of 240. So now our goal is to find, we would like to find the absolute max of v on the interval 0 to the square root of 240. Now, for the progress of this point, this becomes the same exact thing that we did a couple weeks ago, where we had a function. We'd like to calculate the maximum on a closed interval, the absolute maximum. So the first thing that we want to do is we want to find critical values. So we're going to find critical values or critical numbers. So we're going to find critical values. So what this requires us to do is calculate the derivative. So we take the derivative of v. And so if we look back here, our v of x we said was 60x minus x cubed over 4. So we take the derivative of 60x, we get 60. We take the derivative of negative x cubed divided by 4, and we're going to get a negative 3x squared over 4. Now, we look to see where is this undefined. Well, it is defined for all x values. So the only critical values are when we set this equal to 0. So we have 0 is equal to 60 minus 3x squared divided by 4. So we move over the 60. So we have negative 60 is equal to negative 3x squared over 4, multiply this by a negative 4/3, multiply this by a negative 4/3, and what we're going to get is the 3 and the negative 60 will cancel to be a negative 20, and we're going to be left with an 80 is equal to x squared. Now we take the square root of this, and we see that x is going to be plus or minus the square root of 80. Now, obviously, when we look at this value, we get 2x choices, but because we said our feasible domain is 0 is less than or equal to x less than or equal to 240, we know that only x equals the square root of 80 is the only critical value in our interval. So now we can look at our chart where we take a look at what is each of my critical values. Well, the only one that makes sense in this case is square root of 80. We include our endpoint of 0 and the square root of 240. And so we've listed off the endpoints, we've listed off all the critical values, and now for each of these, we're going to plug them back into our volume formula. This will calculate what is the volume of each of these. So if we plug in the square root of 80, we're going to get a 60 times the square root of 80 minus the square root of 80 quantity cubed over 4. This expression we could simplify if we so desire, that we'll have a 60 times the square root of 80. If we have square root of 80 cubed, well, 2 copies will make an 80. And then we're left with the remaining one of the square root of 80 divided by 4. So this would give us 60 square root of 80 minus 20 square root of 80, which is equal to 40 square root of 80. Now, we plug in the other values. These are going to be much easier. You plug in 0, you're going to get 0. You plug in the square root of 240, you're going to get a 60 times the square root of 240 minus the square root of 240 quantity cubed over 4, and this will also end up equaling 0. So we see in this case, the largest overall value we get is 40 times the square root of 80. So what our answer now says is what dimensions will produce a box of maximum volume. Well, my dimensions in this case, we see that x is going to be equal to the square root of 80. And the other dimension, the height in this case, well, we could calculate that by going back to this formula over here. So we could calculate this h would be 60 divided by the square root of 80 minus the square root of 80 divided by 4. And for the sake of simplifying, this is perfectly fine. So these would be our dimensions of our box in this instant, where x corresponds to our base and h corresponds to the height. Come on.